Hello friends, welcome to the new subject Nonlinear Dynamics. We take introduction. In it we will first see the historical perspective. So welcome again to the beautiful world of chaos and fractals. In 1987, James Gleick wrote a book called Chaos. And this book is the bestseller for months. In 1986, Pidgeon and Richer produced a picture book named The Beauty of Fractals. The Beauty of Fractals. And this book is on the coffee tables in living rooms. So, before starting this subject, we should know these chaos and fractals are a part of a bigger subject known as non-linear dynamics. And this subject deals with the behavior of systems that evolve over time. Means, let's say, few state variables that characterize the system may either lead to some equilibrium values or may do some sort of oscillations, and they may exhibit many other sort of behaviors. So these such systems can be studied using this approach called the nonlinear dynamics. So examples of systems like the classical mechanics, chemical kinetics, population biology, neuroscience, and many more. So, the history of dynamics starts in mid 17th century when Newton gave us the calculus, laws of motion, laws of gravitation. And he also discovered laws of motion and gravitation to explain the planetary motion. So, later on in 1800, most of the mathematicians and physicists solved the two-body problem using the inverse square law of gravitation. But Newton's analytical methods to solve three-body problem was not very easy, and eventually it was realized it is impossible to solve the three-body problems. Three-body problems like sun, moon, and earth. Now in 1890s come the Poincare, and he developed a powerful geometrical approach. To analyze questions qualitatively rather than quantitatively. And he is the first person to glimpse the possibility of chaos, in which a deterministic system is exhibiting aperiodic behavior, and that depends very sensitively on the initial conditions. In 1920 to 50, chaos remains at the background, but non-linear oscillators. Non-linear oscillators plays a vital role in development of radio, radar, phase-locked loops, and lasers. From 1920 to 1960, complex behaviors in Hamiltonian mechanics can be understood by using nonlinear dynamics. In 1963, with the advent of high speed computers, with the advent of high speed computers, it became easy to simulate the mathematical models. So, this led to the discovery of chaotic motion on a strange attractor. This led to a discovery of chaotic motion on a strange attractor by Lorentz. We will discuss these concepts later on. And what Lorentz found is that the solutions of the equations never settle down to equilibrium or a periodic state, and they continue to oscillate. So, solutions continue to oscillate in an irregular and aperiodic fashion. And even when initial conditions are slightly changed, the resulting behaviors will soon become very different. So, systems are very much depend on initial conditions. So, role of initial conditions are very important. Lorentz also showed a structure in the chaos when plotted in the three dimensions. The solutions to these equations fell onto a butterfly shaped set of points. You can see here. In 1970, Roulet and Tekens proposed a new theory for the onset of turbulence in fluids. So they used nonlinear dynamics to propose or to understand the turbulence in fluids. And they consider strange attractors in the turbulence of fluids. In 1970s, May found chaos in iterated mappings arising in population biology. In 1970s, physicist Feigenbaum discovered that universal laws govern the transition from regular to chaotic behavior. Some universal laws govern the transitions from regular to chaotic behavior. He also established a link between chaos and phase transitions. Similarly, in 1970s, Winfrey applied geometrical methods of dynamics to biological oscillators. like circadian and heart rhythms. In 1970s, Mendelbot codified and popularized fractals. And he also applied the concepts to mathematical biology. So, thank you. Thanks for watching.